So in that first example, we are talking about horizontal versus vertical in terms of direction. There wasn't anything you had to do. It was just a review of vocabulary, making sure we understand terminology and kind of like what I'm saying when I say the 0.64. The next part was to graph and label each of those points. So when it says to label, you had to put letter A, B, C, etc. So when you graphed the 0.35, you had to give a label of A. When you graphed the point -27, put a letter B, -6, 4, C, 0, -5, D, 3, 0 is E, -3, -6 is F, -6, -5, was G, 2, 7, H, 7, 0, I, 0, 7, -5, 4, 3, 6, 0, 6, and -7, 0. Okay. Today we are moving past what we were looking at previously, which was piecewise functions, and we are looking towards what we call absolute value functions. So in the past, we already solved absolute values. We know that when we solved an absolute value, that it had two solutions depending on where the absolute value was. Sometimes it had one, and sometimes it had none. When you graph an absolute value, we're going to be able to see where those solutions lied on the graph and understand why it had none, one, or two. So the function f of x equals the absolute value of x is known as the absolute value function. The function f of x equaling the absolute value of x is the absolute value function. It is also known as the parent function. The highest of lowest points on the graph of an absolute value function is called the vertex. The highest or lowest point on the graph of an absolute value function is called the vertex. The axis of symmetry of a graph of a function is the vertical line that divides the graph into mirror images. It's the vertical line that divides the graph into mirror images. And an absolute value graph has one axis of symmetry that passes through the vertex. The axis of symmetry passes through the vertex. An absolute value function is learned after piecewise because an absolute value function is actually represented by a piecewise function. So the absolute value of x could actually be written as 3 separate equations. It could be written as negative x, 0, and x for x less than 0, equal to 0, and greater than 0. The absolute value function can be written as a piecewise The absolute value function always graphs as a V. The absolute value function always graphs as a V. So on that graph to the right, you can sketch that graph. And then we're going to talk about the blue, the green, and the purple parts of the graph and how they represent the absolute value. The absolute value function has a domain of all reals. The absolute value function has a domain all reals. The range of the absolute value function is always y greater than or equal to 0. It is y greater than or equal to 0. Its vertex is the origin, 0, 0. Its vertex is the origin, 0, 0. The axis of symmetry is that dashed green line. It is the line that cuts the graph in half. The equation of the axis of symmetry of the parent function is x equals 0. The equation of the parent function is x equals 0. The slope in this case is 1, 1 or negative 1, 1, depending on which side you are looking at. So the slope of the positive side is 1, 1. The slope of the negative side is negative 1, 1. Right? The absolute value function has what we call the transformational form. The transformational form is y equals positive or negative a, absolute value x minus, the minus is part of the equation, h plus k. The negative tells me if the graph is reflected. The negative tells me the graph is reflected, and it is reflected over the x-axis. The a value will tell me if my graph is stretched or compressed. The a value will tell me if my graph is stretched or compressed. The h value tells me if the graph moves left or right. So that's a H for horizontal. So it's the horizontal changes. It's either left or right. And the K value tells me if it moves up or down. And if something moves up or down, we refer to that as vertical. The vertex of an absolute value function, the vertex of an absolute value function is h, k. The vertex is h, k. So it's important to remember that the vertex comes from the movement left or right, as well as the movement up or down. Oops. Reflection. So we talked about the A value. The A value gives me my reflection. So when A is positive, the graph opens up. When A is negative, the graph opens down. So you can see that is f of x equals the absolute value of x, which has a positive A. This is f of x equals negative absolute value of x, which has a negative A. So negative A opens down like a frown, a positive A opens up. The graph can be stretched or compressed based on the A value being a fraction or a whole number. Stretching or compressing does not value if it is positive or negative. The stretching or compressing does not value if it is positive or negative. The graph will be stretched if A is greater than 1. The graph is compressed or made wider if A is between 0 and 1. Our A value acts like the slope. Our A value acts like the slope. So graph the following function, identify the vertex, and describe the effect of A on the graph. So in this case, the A value is a negative 1/2. So my graph is, reflected because of the negative, and the 1/2 tells me that it is compressed. Because the H and K are zeros, like there's nothing being added inside, there's nothing being added outside. My vertex is 0, 0. And for most of what we're going to look at today, we're not moving our graphs left or right. We're just looking at stretching and compressing as well as reflecting. That 1/2 represents my slope. So what that means is from my vertex, I am going to apply a slope of a positive or negative 1/2 from my vertex. And we're going to talk about what that means kind of in a minute here. So the vertex is 0, 0. My slope is negative 1/2 to the right. My slope will be negative 1/2 to the right, meaning it goes down 1 and over 2 to the right of the vertex. Because the vertex is kind of like the breaking point of the piecewise function, because the vertex is like the breaking point of the piecewise function, the y values are going to stay the same, but the x values are going to become their opposites. So at the point -2, -1, we're now going down 1, left 2, down 1, left 2, down 1, left 2. Because my graph is perfectly cut in half at the vertex. So whatever it does to the right, it also does to the left. Okay, the absolute value of x multiplied by 4. So it says describe and graph. So the vertex, once again, 0, 0. The transformations are stretched by 4. So what that means is my slope is 4 for x greater than 0. And -4 for x less than 0, because it all has to deal with the vertex. So if you plugged in 1, you get 4. 2, we get 8. And then the absolute value will do the opposite. -1 is also 4. -2 is also an 8. And again, it all has to do with that the axis of symmetry is x equals 0, which means I could fold my graph in half. Down the line, x equals 0. And whatever happens on the right also happens on the left. You can see how this graph is much more narrow than the regular absolute value. So the original absolute value would look like this. So in black, that's the parent function. So you can see how the blue graph is narrow or stretched upwards. 1/4 x. Once again, our vertex is unchanged because h and k are unchanged. The a value is 1/4. So that tells me that my graph is compressed. So it's now the opposite The last graph was stretched by 4. This graph is compressed by 1/4. So again, thinking of 0, 0 as the breaking point in your table. At 1, 2, and 3, it's increasing kind of by like that 1/4. So you have 1/4, 1/2, 3/4, and then 1. And the same would be true on the negative side. It'd be 1/4, 1/2, etc. So you plot your 0, 0 vertex and apply your slope. And we can once again see that this graph is compressed. It is much wider. The original graph would have been up there. So you can see how the red graph is below it. Do you have this last example? Yeah. Okay. So you have 3/2 absolute value of x. So again, that a value is 3/2 between 0 and 1. No, it's greater than 1. So because it's a fraction, that doesn't mean that it is compressed. Just because it's a fraction does not mean it's compressed. 3/2 is 1.5. 1.5 is greater than 1. Therefore, this graph is stretched. The slope is 3/2. The vertex is 0, 0. So it goes up 3/2. And up 3, left 2. The domain and range of all the last 4 graphs we've done have been all reals, and then y greater than or 0 equal to 0 to infinity. All of the domain and ranges of the last 4 examples have been the same as the parent function. Okay, go ahead and start your homework on that next page. I am looking for something similar to what we have